our reduction potential table as written in the textbook are going to be able to undergo reduction more readily. Now, keep in mind the term oxidizer or oxidizing agent. That's something that is reduced. Okay, and those have the most positive reduction potentials. The strongest reducers or reducing agents have the most negative reduction potentials. So those are sort of the trends. When you're looking at the potential, the reduction potential table, this is a sort of simplified version that's going to try to show you the trend that exists. So those reactions that occur at the top of the table, the one in your textbook that occurs at the top is F2 plus 2 electrons forms 2F minus. F2, our fluorine gas, is the easiest to reduce. Therefore, it's the strongest oxidizing agent. And if we're looking at the reduction potential for this half reaction, I wrote this down. Where did I put it? Here it is. It is 2.87 volts for the F2 plus 2 electrons. So you see a large positive value. Okay. Towards the bottom of the table, we're going to have our species that are most difficult to reduce. There are our weakest oxidizing agents. They're going to have the most negative reduction potentials. And so for this lithium reaction, lithium ion plus an electron forms lithium solid. We're going to have minus 3.05 volts for the potential. Now, we have a species on the reactant side and a species on the product side for each of these half reactions. Notice the relationship, okay? So F2 in this top reaction is the strongest oxidizing agent, so really good at being reduced. On the product side, we have our weakest reducing agent. Okay, so if the thing on the reactant side is the strongest oxidizing agent, the thing on the product side is the weakest reducing agent. Okay. So keep an eye on those trends. Questions on those? All right. So let's think about a galvanic cell with this overall cell reaction of aluminum 3 plus magnesium forms aluminum solid and magnesium ion. There are two half reactions, and you can look up these reduction potentials. That wasn't specified like that as well as I want it to be. Those are reduction potentials for those half reactions. Given those half reactions, I want to calculate or determine the cell potential for a galvanic cell. Okay. Notice with these two half reactions that they're both written as reduction, right? So that's the reduction potential. Right, so both have electrons on the reactant side. So one of these reactions will remain that way, and the other will be reversed. Okay. So one of these reactions will occur at the anode. It'll be the oxidation reaction. The other will occur at the cathode. That'll be the reduction reaction. We have to figure out which one is which. So how are we going to do that? Yeah, Braden? Yeah, well, yes, we can look at this overall reaction, and we'll see that we have the aluminum 3 plus 3 electrons. That's going to show up here. We have magnesium 2 plus on the product side, so that means this reaction gets reversed. So which one is the reduction reaction? Aluminum or magnesium? Yeah, it's aluminum. Reduction is gain, so it gains electrons. They have to show up on the reactant side, which means that the magnesium half reaction is the oxidation half reaction. If we want to calculate E cell, we'll use the equation that we saw last time, which is E cell equals the reduction potential at the cathode minus the reduction potential at the anode. Okay. So which occurs at the anode, oxidation or reduction? Oxidation. And so a reduction occurs at the cathode. And so our E cell is going to be the reduction potential for the aluminum half reaction minus 1.66 volts minus 2.37 volts for the magnesium half reaction. So we have a negative value plus a larger positive value. Well, minus a large negative value, so it's plus a larger number. And so we'll end up with a positive value for our cell potential. And that's what we want to see. Why do we know we want a positive cell potential? Yeah, spontaneous. We have a galvanic cell, we know it has to be spontaneous. And we know the E cell has to be positive. So if you didn't have this overall reaction, would you be able to figure it out? What the cell potential is? Yeah, how would you do that? There's only one way for these two half reactions to be combined to make a positive cell potential. Okay? And so if you're not given an overall cell reaction, you can still figure out the cell potential. Right? You just figure out which value for the reduction potential will go in which of these spots, get a positive value, and then you can figure out which is the cathode, which is the anode. Oxidation occurs at the anode, reduction occurs at the cathode. Does that make sense? Hopefully. The other thing to note, so our electrons aren't balanced in these half reactions as written. Is that a problem? No. So the cell potential doesn't depend on the number of electrons transferred. It's what we refer to as an intrinsic property. So I didn't have to multiply the cell potential by number of electrons or anything like that. I didn't have to reverse any signs, nothing, using this equation. And so the number of electrons transferred doesn't matter. If we've multiplied both of these half reactions by 100, the cell potential is still the same. Okay. So we've been saying that we need to have a positive cell potential to have a spontaneous process, and spontaneous process is going to occur in a galvanic cell. We're now going to actually look at the equations that get us there. Again, recall our equation for cell potential. We just wrote this, but I'm going to rewrite it here because this is written slightly differently than what we just saw, where E cell is equal to the reduction potential at the cathode minus the reduction potential at the anode. And the only difference is specifying that one's an oxidation process and the other's a reduction process. It's just simply interchanging at the cathode and reduction. Okay. So if we have a positive cell potential, we get a spontaneous process, a negative cell potential, we have a non-spontaneous process. And the reason being is the way we relate this to cell potential or EMF, which is electromotive force. I think we used this word last time, this phrase. Your book tends to use it more than I do. So we can relate the Gibbs energy delta G naught equals minus N times F times E naught cell, so the cell potential. N is the number of electrons transferred. F is Faraday constant, 96,485 coulombs per mole. So you can see that constant written down here. That's the quantity of electrical charge on a mole of electrons. That's the Faraday's constant. So now you can see, given this equation, if we have a positive value for our cell potential, overall the right-hand side of this equation becomes negative. And if we have a negative value for our delta G, we have a spontaneous process. Okay? So that's where all of this is coming from, the positive cell potential, galvanic, spontaneous, that's all coming from this equation. Questions on that? Now, because of all of the work we've done in chapter 19, we can relate the Gibbs free energy, the Gibbs free energy we have related in the past to the equilibrium constant K. Now we can relate the cell potential to the equilibrium constant. And so we just saw delta G equals minus NFE. We know from chapter 19 that delta G equals minus R times T times the natural log of K. And so if we set these two equations equal to each other, we can rearrange them and be able to relate the cell potential to the equilibrium constant. So I'm going to write, let's see, which way did I do this here? Minus NFE cell equals minus R times T times natural log of K. Again, just setting those equations equal to each other, so they're both equal to delta G. Now, if we want to isolate the cell potential on one side of the equation and the equilibrium constant on the other, we can divide both sides by minus N times F. And we'll get E cell equals R times T over N times F times the natural log of K. Negative signs cancel out. Oftentimes, we don't use the natural log, we use the log base 10 form. And we may recall that 2.303 times the log of some value x is equal to the natural log of that value. So I'm rearranging this again to get us to what's called the Nernst equation, which is a really useful, powerful equation. Okay. So I'm going to end up plugging this in for natural log of K. It'll be 2.303 log of K. But the other thing I want to note is that normally we're working at 25 degrees Celsius, correct? So, or 298 K. We can assume, for the sake of simplicity, that our equation, or our cells are going to be operating under those conditions. Plug that in for T, and then we're going to end up with a nice constant. Okay. The cell potential is equal to 2.303 times R times 298 over N times F log of K. And all of this then becomes a constant. Okay, as long as we're at 25 degrees Celsius, we end up with E cell equals 0.0592 over N times the log of k. We need to keep n here because we need to, it depends on the number of electrons transferred. Okay. That doesn't get lumped into a constant. But the R, T, and Faraday's constant do. So this gives us a Nernst equation, the Nernst equation. Okay. It's going to allow us to relate the cell potential to the equilibrium constant. The only other thing we need to know is the number of electrons transferred during the redox process. And we have to make sure we're at 298K, but like I said, typically we are. Everyone okay with that? That algebra? Is that a question? Yeah. 2.303 times the log of some value x is equal to the natural log of some value x. Yeah, so that's coming from this. Other questions? Yeah.
Do we need to know the bottom part, or can we just know the set E cell equals RT over?
Yeah, if you want to plug in all those values, you're more than welcome to. I can't recall which equation you're going to get on the exam, but they will both work as long as you're at 25C. Sometimes this is a little quicker. You already have everything all multiplied out. Other things? Okay. All right, so let's do an example. We have a galvanic cell that has these two half reactions. There's a chromium half reaction and a copper half reaction. The reduction potentials are given. That would have come from the table. Let's calculate the Gibbs free energy and the equilibrium constant. But the first thing we need to do before we do any of that is to write the overall cell reaction. I'll let you guys work on that for a couple minutes. The groaning actually makes me feel like this is the right choice. some good work, good questions. Thank you. All right, so my approach for this, for figuring out, first thing I want to do is figure out which of these half reactions I need to flip, right? Which one's going to be the reduction half reaction, which one's going to be the oxidation half reaction. And so I'm going to look at my equation for the cell potential. Okay, and I'm going to figure out which way I can rearrange these values for the reduction potentials for these half reactions to get a positive cell potential. So the only way to do that is if I have my 0.34 volts minus the negative 0.74 volts, which means that reduction occurs at the cathode. So this has to be the reduction reaction. Reduction is gain of electrons, so that is the reduction half reaction. That's as written. Oxidation occurs at the anode. The oxidation half reaction has to be the chromium half reaction. So this one is going to be reversed. Okay. But overall, our cell potential, we're going to need this in a little bit here, is 1.08 volts. Okay. So just summing those values. So now that I've done that, I know which is the oxidation, which is the reduction half reaction. Now I can go about doing the balancing and adding these equations together and figuring out the number of electrons transferred. So luckily, these half reactions are relatively easy to balance. So I'm going to reverse this chromium half reaction. Okay, because that's oxidation, loss of electrons. Electrons have to show up on the product side. The copper half reaction, I'm going to write this way. That's the reduction. If we're thinking about how to balance this, all of our atoms are balanced. The only thing that isn't balanced is the number of electrons. Okay? So we do need to balance those before we can write the overall cell reaction. And so we're going to multiply the chromium half reaction by 2 and the copper half reaction by 3. I'm going to rewrite both of those. We're going to get 2 chromium. I'm going to leave off my phases at this point. 2 Cr3 plus 6 electrons. For the second half reaction, I'm going to have 3 copper plus 6 electrons forms 3 copper solid. Sorry, I missed a charge. 2 plus. Okay. Everyone okay with that? So our 6 electrons cancel. Those are the number of electrons transferred. So we sum these up to get our overall cell reaction. 2 Cr plus 3 copper 2 plus forms 2 chromium 3 plus and 3 copper solid. Again, leaving off phases even on this. Okay, questions on balancing that? All right. On the next slide, okay, so then the previous slide, our overall cell reaction. I think for these types of problems, figuring out that overall cell reaction, number of electrons transferred, that might be the hardest part. The rest of it's just plugging values into the equation, making sure your units are correct. You good? when we go back to balancing the equations, to find N, to find the moles of electrons transferred, that's going to be equal to the number of electrons that are crossed out when you balance up and add those equations. Yep. We are going to use the same reaction, and now we're going to calculate the Gibbs free energy for for the overall cell reaction. We already calculated our E cell, and it was 1.08 volts. So that was kind of nice to get that out of the way there in the first step. And again, the number of electrons that get canceled when we're adding up the two half reactions to make the overall cell reaction, those are the number of electrons transferred. That's what's N here in this equation, okay? And so our delta G equals minus NFE minus 6 times, I always forget this value, 96485. Coulombs per mole electrons. And then the cell potential is 1.08 volts. 1 volt is 1 joule per coulomb. So I'm going to use those units there. And you'll see that coulombs are going to cancel. The moles of electrons cancel with N, moles of electrons. And so we're left with our answer, our Gibbs free energy in joules. Okay. And I get minus 6.25 times 10 to the 5th joules. Questions on that? Okay. Yes? Yep, I'll go back one more. Are we good with this slide? No? You're good? Okay. Yep. Okay. Now our last step is to calculate the equilibrium constant K. We can use either equation. Delta G equals minus RT natural log of K, or the cell potential equals minus 0.0592 over N times the log of K. Your choice. I will, what did I do? Did I do both? Yes, I did, so I'll write out both. So if we use the delta G equals minus RT natural log of K, we take our value that we calculated on the previous slide, which was minus 6.25 times 10 to the 5th joules, equals minus R, which is 8.314 joules per mole Kelvin, times the temperature in Kelvin, 298 K, and then natural log of K. Looking at our units, everything should cancel. Is that right? I think our moles aren't. That's okay, we're not going to worry about that. Okay, so rearranging everything, we're going to get K is equal to E, the 252, something like that. I didn't actually figure that out. Oh, that's why. You get an overflow error. You get a big number, okay? if we use our E cell, the Nernst equation, E cell equals 0.0592 over N. Our cell potential was 1.08 volts, equals 0.0592 over 6 times the log of K. And rearranging that, we're going to get 10 to the 109 equals K. Another big number. Okay. So I'm satisfying that I can't calculate those, but sometimes that happens. Questions on those? Yes? You don't always get an overflow. Actually, that one might work. Nope. So I don't think we'll put an overflow. That's harder, multiple choice question. And the error if it was a fill-in would be a little bit off. Yeah.
How do you find the n value again?
Yeah. So n. Other things. Okay. So, given all that we've just looked at, we can kind of summarize the effect of stoichiometry on our different values here for E cell, for delta G, and for our equilibrium constant K. So if we multiply that overall cell reaction by a factor of 2, the one that we just worked on, what we'll end up seeing is that we'll then have 12 electrons transferred. Okay? How will the cell potential change? It doesn't change, okay? So doesn't depend on stoichiometry. When we added our two half reactions together, we had to multiply each half reaction by a factor in order to get the electrons to transfer. We didn't multiply the reduction potential by anything, right? So we don't have to do that. The reduction potentials, the overall cell potentials do not depend on stoichiometry, so there's no effect if we multiply by a factor of 2. For delta G, this does depend on the number of electrons transferred. Because delta G equals minus NFE. So if we increase the number of electrons that are transferred, delta G increases. So delta G increases as the number of electrons transferred increases. Yes?
Wouldn't it be getting more negative though?
Well, okay, yes, good point. More negative. Yeah, we'll do that.
So it would like be going lower and lower.
Yes. More negative. Larger magnitude. More negative. Same with K, our equilibrium constant. You can look at this in two ways. Using the Nernst equation. If we multiply both sides of this equation by n times the cell potential was 0.0592 log of K. If n increases, K has to increase. And then you can also relate this with delta G. Since delta G equals minus RT natural log of K. If delta G increases, K has to increase. Or the magnitude becomes more negative, K has to be larger. So I guess really main thing here, cell potential does not depend on number of electrons transferred. Okay. Questions on any of that? Okay. That is all we have for today. So enjoy your extra 10 minutes.